In this, the fourth and last video of the ECOFusion webinar, we will cover some summary topics. First, we'll look at some predictions on Q, the ratio of energy out divided by energy in. Then take a look at some path to improving that in the future. Emphasize the fact that ECOFusion enables the dream energy source of taking pure deuterium to pure helium-4, and wrap up with some summary comments on the ECOFusion program. A prediction on Q has been done for the non-optimized design. This is the design that was thoroughly studied. Each design takes at least 6 months to go through in detail, and so therefore we have stopped our analysis at this point since the experimental apparatus can now be built. Once the experimental apparatus is built, it will be far quicker to turn knobs to optimize the device than it ever would be to go through many 6-month iterations at trying to make some predictions on the ultimate performance of the device. Here we can see that for that non-optimized design, we've already got a very good result. The Q scientific is given as almost 4. We've got a power out of 58.4 kilowatts per cell, and then we've got power inputs that come from the ion beam and electron beam drive powers. One comment of note is that we will need permanent magnet solenoids to achieve this value of Q, but that of course is merely a detail and is straightforward to achieve. Although the nominal design already predicts 4 times more energy output than is required to run the device, there is a known path to improving this even further. 2 considerations that guided the nominal design were electron scattering and self-magnetic fields. The electron scattering in the merge region has led to a design choice that has beam energies significantly higher than that of the maximum cross-section. By going to somewhat lower energy, improvements in device operation are expected. The self-magnetic fields of the beams are presently well handled, and increasing these currents would also lead to additional device improvement. Ion microscopy techniques could allow for compensation of beam aberrations, leading to a smaller spot size in the overlap region, which in turn would lead to increased output power. A last known path to improvement lies in using 1 interaction region rather than 2 in the overlap region, since this would eliminate the upstream momentum increase, which in turn would lead to additional output power and less beam halo. There is also an unknown path to device improvement. While the analysis has been quite detailed, the goal of the analysis was to overestimate problematic effects wherever an exact determination was not possible. Hence, the halo may not hit exactly where the modeling predicts. Also, it may turn out that the ion currents do not fully match the electron currents once the first experiments are done. Other unforeseen issues and opportunities may arise as well in the real working device. But the main point is that once the prototype is built, we can experiment and measure and then correct. Wherever the halo hits, we can redirect it. If we need a different electron beam current, we can supply it. The ECOFusion paradigm includes the enormous advantage that we can always work both on increasing the energy output as well as decreasing the energy input. And a Q of more than 10 should certainly be achievable fairly quickly after the first few prototypes are constructed and optimized. One of the great advantages ECOFusion has over other fusion approaches is that it will allow the ultimate goal of obtaining a power source that takes pure deuterium and converts it to pure helium-4. This would allow use of the deuterium present in enormous quantities in seawater without being concerned about the amount of the proper isotope of lithium that is needed to generate tritium for the deuterium-tritium fusion designs. As a first step in seeing how this is possible, note that the design presented here is also appropriate for a deuterium helium-3 reactor. The cross-section is about the same, but there would be more problems with space charge, recombination, and charge exchange of helium-3 than there is for tritium. The deuterium-helium-3 reactor will be an extremely good choice for testing as well, since there are no neutrons or tritium, meaning that it is extremely safe. The ultimate goal is to have a deuterium-deuterium reactor at a central location that is used to produce tritium and helium-3. The tritium would be used at the central location with a deuterium-tritium reactor to power the deuterium-deuterium reactor, as well as to provide additional power at that central location. Then, deuterium-helium-3 reactors could be placed in communities throughout the world due to the very safe nature of the deuterium-helium-3 reaction. Now we'll close with some summary comments. ECOFusion, a new approach toward fusion energy generation, has been proposed to you today. The proposal uses colliding beam devices that can be built with materials and technologies that are available today. An output power per cell of about 50 kilowatts is predicted from the present design, but improvements in spot size and lower energy could increase this to 300 kilowatts. Calculations predict an engineering queue that is already good enough to consider for use in a power plant. While the device may seem expensive now, since we're talking about a storage ring, note that $300,000 is a lot of material, and these storage rings are extremely small by particle accelerator standards. It's also relevant to note that cars are now built for a mere $10,000 and that the first transistor was quite large and expensive too. Technologies have a way of evolving over time to make things far cheaper than the first prototype ever is. Advantageously, ECOFusion holds out the promise of using a pure deuterium source as fuel, implying a limitless supply. The theoretical analysis has been extremely extensive, although it's only been done by one man, so it is now time for a serious review. It is also time to begin work on prototype construction and testing. We'll close now with another look at the ECOFusion device.